Hello, I'm Kevin Yu, and I'll be talking about optimal transport and its applications in image processing and computational photography. So to begin, let us consider two images which can be represented as two probability measures mu and nu. And our question is, what is the image in between mu and nu? The most common answer we get is a per pixel linear interpolation. However, this isn't quite as ideal. Let's suppose we have two images of two balls in two different locations. A per pixel interpolation would result in us having the ball disappear at one position and reappearing in the other. We want something better. We intuitively want an image that has the ball moving across the screen. So we need some sort of spatial dependency. So to do that, we could define a distance called the Wasserstein distance, or the Earth mover's distance, that measures the distance between two probability measures. In the sense that, supposing that there are two measures, how can we find a coupling of the measure that intuitively transports the mass from one measure to the other in a way that minimizes some distance? And it turns out that the probability measures endowed with this metric is a geodesic measure space. So it is possible to find geodesics. And it turns out that geodesics in this space are what we expect. So when we have two measures of two balls in different positions, we would get a ball translating from one position to the other one. So this is in a sense the right distance to use. We'll talk briefly about optimal transport. So given two probability measures and a non-negative cost function, the Monge problem asks to seek for a function that moves mu on nu in a way that it minimizes the total costs needed. This problem isn't quite straightforward to solve since the constraint is not convex. So we instead consider the Kantor-Rubich problem, which asks instead for couplings, which can be thought of as a matrix that describes from each point in mu how much mass to move to nu, and then you find the total cost over that. And this is better because this is a convex problem with this has a convex constraint, so this always has a minimizer. Now, the Kantor-Rubich problem is still not quite as easy to solve, so instead consider regularization term, which is a term of the KL divergence of the coupling with respect to mu cross nu. And this turns the objective function into a strictly convex one. So there's always a unique minimizer, and there's an algorithm to solve this problem called Sinkhorn's algorithm, which is very fast and easy to code up. So let us talk about color grading right now. So color grading in a brief sense is to suppose that we have two images, one input and one target. We want to change the colors of the input image to match that of the target image. So how can we do that? So a traditional technique is to use histogram matching, which looks in each channel separately, and it orders all the colors, and it pairs up colors with the same order. So this actually does minimize the one-dimensional optimal transport cost for any strictly convex function. And using optimal transport, actually, we can naturally generalize this to over multiple channels simultaneously. How do we match colors by a function such that it minimizes the distance between the function we are moving colors? And there are also some minor considerations that I work to address in this project, including how do we sample points on measures, since we can't work over the entire image, and what color space we're working over, and how we want to filter the end result. So here's an example of an input image and a target image. And here are some results while varying epsilon, which is the regularization term. So it turns out that for small epsilon, there's a lot of strong artifacts, but for large epsilon, the image turns blurry. So you want a small epsilon of roughly 0.01, which is good. We can also test how different color spaces work. By matching in the RGB space, we tend to get not as ideal colors as in the LAB spaces, which makes intuitive sense since colors are more perceptually uniform in LAB spaces. And finally, we can filter the end result to get some cleaner images, and we can do this by both a bilateral filter and a joint bilateral filter by using the input image as guiding. And usually bilateral and joint bilateral perform pretty close. Here's another example of color grading. And now let's talk about non-photorealistic rendering. So given again a color histogram, which is a probability measure, mu, and we want to find some mu hat that empirically approximates mu. And now the question is what distance we want between mu and mu hat. So we could use the Wasserstein distance, but like the counter-voltage problem, it's not so easy to compute. So we can instead consider the sinkhorn divergence, which is defined through the regularized problems. And this is very interesting as it approximates the maximum mean discrepancy for large epsilon and Wasserstein distance for small epsilon. And in general, for larger epsilon, the convergence of the calculation and convergence is easier. But for smaller epsilon, the support of mu is better recovered by mu hat. And yeah, so we gradient descent on the sinkhorn divergence to find a mu hat. So here's an input image, and then we found mu hat with k equals 30, and we converted all colors to colors from mu hat, which is shown in the non-photorealistic render. And then we can do some smoothing by a joint bilateral filter to obtain the right image. Here's another example. Here's some more examples using images that are not mine. Yeah, and I think this gives some pretty nice results, and this approach is original as far as I know. Here are my references. And that is the end. Thank you.